Welcome to MetaMinds Academy. From this video onwards, we are going to solve partial differential equations. In this video, we are going to learn how to solve a partial differential equation, and we will solve a good number of problems in this video. So the method of obtaining general solution. So this is the method of obtaining the general solution of a partial differential equation. In this step 1, you are given the equation, partial differential equation. You rewrite the differential equation in this form: a function of xy into p, or a function of xyz into p, plus a function of xyzq into small q, lowercase letter q stands for dou z by dou y, small p is dou z by dou x, equal to a function of xyz. And then you write the Lagrange's auxiliary equations. They are dx by p. What is p? P is the quotient of dou z by dou x. dy by q, the function q, equal to dz by r. So once you write the auxiliary equations, Lagrange's equations, solve these simultaneous Lagrange's auxiliary equations to get the solution of the form u of xyz equal to c1. Right? You can consider any two of these equations, and you make these two equal, you will get 1. If you make these two equal, you may get 1. You make these two equal, you will get another one. So you choose two functions u and v. They are solutions of integrating. Solutions obtained by integrating the pairs of these equations u and v, and you write the solution as f of u equal to 0. You can also write this as u equal to f of v or v equal to g of u, one as a function of the other. Here what are u and v? U and v are linearly independent functions. U and v must be linearly independent functions. That means what? U by v is not a constant. That means one function is not a constant multiple of the other. That means you cannot write u as a constant multiple of v or v as a constant multiple of u. Right? You should not be able to write like this. In that case, they become linearly dependent. If you can write u equal to constant into v, or v equal to constant into u, then u and v become linearly dependent, and we have to search for one more linearly independent solution in that case. So we need two linearly independent solutions to find the general solution of the equation. Okay. Now there is a concept like Lagrange's multipliers. In this, we consider the auxiliary equations, Lagrange's auxiliary equations, or subsidiary equations also they are called. Right? Now you take any functions p1, q1, r1. They may be functions of x, y, z, or they may be constants. You can take them conveniently as required to make this integrable. Right? To make this integrable. So you multiply numerator and denominator by p1, multiply this by q1, multiply this by r1, and then add. Right? By componendo and dividendo, this ratio must be equal to this ratio. So this equation 1 is equal to, that means all of these three fractions are equal to the fourth fraction. That means you can write this here in continuation. So whenever it is not possible to integrate directly by taking any pair of auxiliary equations, we go for this by componendo and dividendo, so that we will get a convenient form of function to integrate or to obtain the solution. If you can choose p1, q1, r1, so that p1 p plus q1 q plus r1 are equal to 0. Sometimes this denominator becomes 0. In that case, you can make the numerator equal to 0 and then integrate to obtain the required solution. Okay. Now let us solve some problems based on Lagrange's multipliers method. Now this is the given equation xp plus yq equal to 3z. How to solve this? Now given equation is xp plus yq equal to 3z. Name it as 1. Write the subsidiary equation because this is already in the form of a function of xyz into p plus function of xyz into q equal to function of xyz. Right? It is already in the required form. So you need not rearrange this equation. Directly you can write the auxiliary equations. Here dx by p. What is capital P? Capital P of xyz is x. The quotient of small p. Right? Capital Q of xyz is y. R of xyz is 3z. So dx by p, capital P equal to dy by q equal to dz by r. So these are the auxiliary equations obtained. Now how do you solve these equations? You take any pair of equations, you will get the solution. Right? So let us take dx by x equal to dy by y. So just integrating on both sides, what you get? Integral dx by x equal to integral dy by y, because it is already in the variable separable form. So here integration is log x, here you have log y, and you write log c1. So you can write it as x equal to c1y or x by y equal to c1. Here u of xyz is x by y equal to c1. Now you take the other pair, this one or this one you can take. Let us take dy by y equal to dz by 3z. Now you can take this 3 here for convenience. Now integrating on both sides, 3 into integral dy by y is integral dz by z. So this is log y, 3 log y equal to log z plus log c2. So this is log y cube is log c2z. So y cube equal to c2z or y cube by z equal to c2. So therefore you have two functions u of xyz is x by y equal to c1. First one, v of xyz is y cube by z equal to c2. What is the general form of the general solution? F of u v equal to 0 or v equal to f of u also you can write. That means y cube by z, v is y cube by z, right? Equal to f of x by y you can write. This is the general solution of the given partial differential equation. Okay, we will go to another problem. Now let us take the problem p minus q equal to ln x plus y. So how do you solve this? Here this is again in the form of p into p plus q into q equal to r. Here p of xyz is the coefficient of small p, which is 1. Q of xyz is minus 1. R of xyz is ln x plus y. So the auxiliary equations are dx by p, capital P, 1, dy by capital Q, dz by r. Capital R is ln x plus y. Now we consider the first two, which are dx by 1 equal to dy by minus 1. So dx is minus dy. Integrating on both sides, you get x equal to minus y plus c1. So that x plus y equal to c1. Right. Therefore, u of xyz is x plus y. Coming to the second one, you consider the first one and second one, last one are this pair. Let us say dx by 1 equal to dz by ln x plus y. These two. Here the problem is, you have no problem with dx because you can integrate. Integral dx is x. But here, to integrate dz by ln x plus y, you should not have x and y here. Right? We cannot integrate this. When you have dz, the function should be in z. Or you can have a constant. But you have x plus y here. X and y are involved here. You cannot integrate this part. But from the first part, you have x plus y equal to c1. Therefore, dx by 1 equal to dz by ln c1. You can replace x plus y by c1 from the first part. So this can be written as ln c1 dx equal to dz. Now integrate on both sides. Ln c1 is a constant into x equal to z plus c2, which is ln c1 into x minus z equal to c2. Therefore, what is v of xyz? The second linearly independent function is, what is c1? You have to substitute it back. So it is ln x plus y into x minus z equal to c2. So that is v of xyz. So therefore, the general solution is f of u comma v equal to 0. That means you can write x plus y comma x into ln x plus y minus z equal to 0, or you can also write v equal to f of u. That means what is v? X into ln x plus y minus z equal to f of x plus y. What is u? U is x plus y. Right? So, or you can also write, because solving the partial differential equation or any equation, differential equation, is obtaining the function dependent variable z. Here we are able to obtain it directly, explicitly. Z equal to x into ln x plus y minus f of x plus y. So that is the general solution of the given differential equation. Okay. Now you take the problem z into z square plus xy into px minus qy equal to x power 4. Now we have to rewrite this equation in the form of p into p plus q into q equal to r. So you have p here, small p, you write, multiply this by this, it is z into z square plus xy into x into p plus minus we have y into z into z square minus xy into q equal to x power 4. So what is capital P here? Capital P of xyz is xz into z square plus xy q of xyz is minus yz into z square plus xy, and what is r of xyz? It is simply x power 4. Now we write the Lagrange's auxiliary equations dx by xz into z square plus xy, dy by minus yz into z square plus xy equal to dz by x power 4. Now you take the first pair like this dx and dy combination, dx by xz into z square plus xy equal to dz by dy by minus yz into z square plus xy. You take this pair, here z square plus xy gets cancelled, z cancelled, and what you get? Dx by x equal to minus dy by y. Now integrating on both sides, what do you get? Log x equal to minus log y plus log c1. So log x plus log y is log xy equal to log c1, or xy equal to c1 is the first solution. So what is u of xyz here? xy, which is equal to c1. Now consider the second pair of equations, either this pair or this pair. Let us take the first one, dx by xz into z square plus xy equal to dz by x power 4. Again you see, you can we always try for variable separable. All x you take it to the left hand side, it is x cube, x power 4 dx by x z into z square plus xy into dz. So we tried to bring all the variables, relevant variables to one side, variable separable method, but you have xy here, beside dz you have xy, so that you cannot integrate. As we said in the previous problem, we have from the first part we have xy equal to c1. So replace xy by c1 here. What do you get? X cube dx equal to z into z square plus c1 dz. So x cube dx is z cube plus c1z dz. By integrating on both sides, what do you get? X power 4 by 4, z power 4 by 4 plus c1 z square by 2 plus c2. But we have to eliminate c1. Finally, it is x power 4 by 4 equal to z power 4 by 4 plus, what is c1? xy. xy z square by 2 plus c2. I write c2 by 4 here for convenience. So you take LCM, 4 gets cancelled, x power 4 equal to z power 4 plus 2xy z square plus c2. Therefore, v of xyz is x power 4 minus z power 4 minus 2xy z square equal to c2. So therefore, this general solution is f of uv equal to 0. That means you can write f of xy comma x power 4 minus z power 4 minus 2xy z square equal to 0, or you can also write the general solution as v equal to f of u. That means x power 4 minus z power 4 minus 2xy z square equal to f of xy. So both are valid solutions. Okay. Now let us take the problem xzp plus yzq equal to xy. So how do you solve this? See, in partial differential equations, every problem is different. Though there is a algorithm to solve the problems, every problem is of different type. Right? I am trying to solve different types of problems, and this belongs to another type of problem. Like you see, here the coefficient of p is xz, so I am directly writing the auxiliary equations dx by xz equal to dy by yz equal to dz by xy. Now you take the first pair dx by xz equal to dy by yz, zz cancel, dx by x equal to dy by y. So integrating, what we get? Log x equal to log y plus log c1, or x by y equal to c1, which is u of xy z. So we got u. Now take the second pair, add first one and last one, dx by xz equal to dz by xy. So here xx cancelled, but dx by z equal to dz by y. So we always look for variable separable possibility, but here what we get, y dx equal to z dz. You have z beside dz, but there is y beside dx. Here we cannot integrate, right? So this way of solving the problem is not correct. In that case, we have to think of the other possibilities, like you multiply here numerator and denominator by y. See, in the denominator y is missing. So that means we are going for Lagrange's multipliers. Y dx by xyz. You multiply this by x dy by xyz equal to z dz by xyz. Now we have some standard formulas here. D of xy is x dy plus y dx, UV rule. So you have y dx and x dy. So you add these two numerators. What you will get? Y dx plus x dy by xyz plus, you have to add the denominators also, xyz equal to z dz by xyz. So here this is 2xyz. Here also you have xyz. You multiply numerator and denominator by 2, gets cancelled. xy 2xyz cancel. Y dx plus x dy equal to 2z dz. This you can write it as d of xy by this method, by this formula, which is 2z dz. Now you integrate on both sides. What do you get? Here integral of the derivative is the function itself, and 2 into z square by 2 plus c2. So we have got the second possible solution, xy equal to z square plus c2, which is v of xyz is xy minus z square equal to c2. Therefore, the general solution is f of uv equal to 0, that is f of x by y, comma xy minus z square, xy minus z square equal to 0, or you can also write u equal to f of v, x by y equal to f of xy minus z square, or you can also write v equal to f of u like xy minus z square equal to f of x by y, or z square equal to xy minus f of x by y. This is most convenient form of the general solution. Here you are obtaining z square, z explicitly in terms of x and y. This is most required general form of the given solution of the given equation. See, this one is ruled out here. We cannot proceed like this in every problem. Okay. Thank you. The continuation of solving these type of problems in the same method will be covered in the, some more problems we are going to cover in the next video. Okay. Thank you.